Okay, I think I can get started now. So welcome everyone to the first webinar presentation from the ATSE Victorian Division Committee for 2023, entitled The Quantum Revolution, Challenges and Opportunities. To start, the Academy acknowledges the custodianship of the lands and the waters on which we all meet for today's seminar. In my case, that's the Wurundjeri Wurrung people of the Kulin Nation, and we acknowledge the traditional owners and pay respects to their elders. We also look forward to the recognition of a voice to Parliament through the referendum later this year. But tonight we'll hear from a panel of three leading experts in the field of quantum technology. Without quantum physics, there would be no internet, computers or magnetic resonance imaging. Now science can unlock unprecedented capabilities to isolate, control, and sense individual quantum particles, such as electrons and photons. Commercializing these technologies will create a new high-growth industry with potential to create jobs and economic opportunities across a range of industry sectors. Of course, this is not without its challenges. And to explore these issues, it's my great pleasure tonight to introduce our panelists. You'll have detailed bios in the program flyer, so I'll just keep this brief. So if I can introduce all three speakers first before we shift to their presentations. Our first speaker will be Professor Lloyd Hollenberg, Deputy Director of the Centre for Excellence for Quantum Computation and Communication Technology. Lloyd is the Thomas Baker Chair, Laureate Professor and Director of the IBM Quantum Hub at the University of Melbourne. Our second speaker will be Professor Eleanor Huntington, Executive Director, Digital National Facilities and Collections at CSIRO, and Non-Executive Director on the boards of ATSE, Industry Innovation and Science Australia, Questacon and Porcelain Supercomputing. And the third speaker will be Dr. Marcus Doherty, Senior Fellow at the Physics Education Centre and the Department of Quantum Science and Technology at ANU, and he's co-founder and Chief Scientific Officer at Quantum BRILLIANCE Proprietary Limited. So the plan tonight is that each of our panelists will give a short 10-minute introductory statement, and then we'll have about 15 minutes of discussion, but then we'll have more time after that for questions from the audience. So please, as they're presenting, don't feel you've got to wait till the end. Please put your questions into the Q&A function. Please use that function and not the chat function, and we will get to your questions towards the end of the hour. So I'm now going to hand over to our panel and initially to Lloyd Hollenberg. So over to you, Lloyd.
Okay, thank you very much, Sandra. It's a pleasure to be here. Let me just organise myself here and bring up the short presentation, don't worry. Okay, so hi everyone, Lloyd Hollenberg from the University of Melbourne, and I will just introduce very quickly the broad area of quantum technologies, and then I'll focus on quantum computing, and I think we've all got our own particular focus here, so let's see how we go. Okay, so what is quantum technology? This is an often asked question. And although you might not realise it, we've already been through a quantum revolution, what people often refer to as the first quantum revolution. And this is for technology that, and Sandra mentioned some of these things like MRI, transistors in all the devices that we use, generally operate because we know about quantum physics, and that quantum physics has led to these technological developments. And if you look at MRI, images are basically formed from the measurements of the quantum properties of protons, for instance, but not individual protons. Protons are in an ensemble of many, many billions. So some key quantum effects are not really exploited. It's led to remarkable technology, but we distinguish this form of technology that does rely on the quantum properties of many particles from the sort of quantum technology that we talk about now, which is sometimes referred to as the second quantum revolution or just the quantum revolution. So that puts it in a bit of perspective, I hope. So here we're really talking about the control over individual quantum objects. Now, these might be natural particles like electrons and atoms and photons, or they might be engineered quantum objects, such as superconducting circuits, which form the basis of some forms of quantum computers. Quantum technology at this level, where we can harness individual quantum objects and control them, and more to the point, encode information on these objects, will lead to some very powerful applications of this technology. And this could be transformative in a range of application areas. So before we drill down into quantum computing, we generally see quantum technology splitting into basically at a course level 3 pillars, although there are connections between these directions of quantum technology. The first one, in no order of importance, quantum computing. The next is quantum sensing and quantum communication. So I'll talk about quantum computing a little bit. But quantum sensing is basically using the properties of these quantum objects in order to sense things at smaller scales and much more sensitively than you could with conventional sensors. And quantum communication also uses the information that we can encode on quantum objects in a way that allows you to transfer information in highly secure ways. Okay, so quantum computing. So I won't go into how quantum computers work, although I'm delighted to, and go on for hours if need be. But basically, quantum computers encode information on individual quantum objects, quantum bits or qubits, and they process this information via the rules of quantum mechanics. And so there are the basic properties or phenomena of quantum mechanics, such as superposition, entanglement, and measurement collapse that come into play. And this means that you can define algorithms that can solve problems potentially faster than conventional computers, perhaps more accurately, or with less energy expenditure. So people are very excited about this, particularly as we have witnessed Moore's law operating for several decades now, and we're getting down to the end of how small you can make conventional transistors. So there's a natural step here to the quantum realm. People have been looking at quantum computing for many decades, of course, and we actually know a fair bit about the sort of applications that we might be able to expect. Of course, there has to be a confluence of this sort of idea of the algorithms we can run and the hardware that people can make. But quantum computers, once they're built and fully operational, are expected to have impact across virtually every sector where you can imagine computers being used. But let me give you a few of the highlights that have been in the news over recent years. The first one I'll mention is this result from 2019. Google produced this quantum supremacy work, which was basically a quantum computer simulating itself and being raced against a supercomputer simulating the quantum computer. And it was found that the quantum computer, Google's 53 qubit machine, could produce data to basically describe the output of random programs in a matter of minutes, whereas the supercomputer would take days. So there was a clear disparity there in the performance of this very rudimentary quantum computer and, a very powerful supercomputer. Soon after, there was a similar result in 2020 from the University of Science and Technology in China. And this was a quantum computer of some 100 qubits in a photonic hardware. And here they were solving a similar problem of producing output, a probability distribution from the quantum computer, but it was what's called the Gaussian boson sampling problem. And there the disparity they were claiming was some 600 million years between the few minutes it took for the quantum computer to produce useful output compared to, I think this was calculated for Fugaku, which is the most powerful supercomputer. So that was a very interesting and startling claim. But from here, the key technical challenges for translation are basically these. So first of all, of course, we have to build sufficiently good hardware and software, continually improve both, in order to demonstrate some form of quantum advantage on a real-world problem. So these previous examples were for rather esoteric problems, or in the case of quantum supremacy, a sort of a toy problem. But really, all the eyes are on whether or not and when we can get quantum advantage on real-world problems. I think most people believe that in the case of a fully functional quantum computer, this will happen. The question is, at what level does the hardware need to be in order to demonstrate this? And I think there's a lot of debate around that issue. We can go into that a bit further if you like. Of course, in order to do this, you can't just have quantum physicists and engineers working on this. You really need very strong engagement with the end users, the people who know about the problems that are being solved, and they know how to eke the best out of conventional computers and can inform how you benchmark and improve the quantum algorithmic approach to these. And of course, in all of this, a great challenge is establishing the quantum-ready workforce. Programming a quantum computer is not just like a different type of statement in a C program. It really, in order to get quantum advantage, is going to require a very deep knowledge of how quantum information actually is processed in order to capture that advantage in the near to mid-term. So what's happening globally? Well, lots, of course. From my perspective, I've been watching as countries are starting to establish facilities at a national level, and I think that'll key into some of our discussion. There are lots of references on this, and you can see this happening in the US, China, the UK, Germany, and so forth. And associated with that is a frenetic amount of activity in the startup space. It's quite incredible. And here's a great series, 2 graphs that I've taken from the ATSE report. And this shows the activity sort of pre-2015, split across software and hardware and corporates and startups. And you can see it's fairly sparse, and it's the usual people that you would expect there. And just a few years later, this is 2020, and this now would be vastly out of date, I suspect. You can see that it's heavily populated, particularly in the startup space, and not just across the software, but also in hardware as well. There are various global initiatives, and I'm part of the Global IBM Quantum Network. We established a quantum hub at the University of Melbourne, which means that we have access to state-of-the-art quantum computer systems from IBM. And you know, for me, I'm a great believer in access to the technology. The state-of-the-art is really important because it's a key driver of innovation. To have access to the actual devices and to know their limitations, their strengths and limitations, is really important for being able to reach that milestone of quantum advantage. So in terms of national activity and national priorities in quantum computing, you can list some generic ones here and kind of map them over to what's happening in Australia. And this is not a complete set of dot points, but obviously in every jurisdiction, the development of quantum hardware is really important. And that could be through installation from trusted providers, or indeed a development of sovereign capability. In Australia, we have quite a bit of activity in this regard. We have, well, Marcus from Quantum Brilliance, and we have other startups as well, Dirac and Silicon Quantum Computing. Another key aspect is the development of quantum software capability. And indeed, part of that is the end user engagement that I was talking about. And again, here we have a lot of activity across the universities and initiatives such as the IBM Quantum Hub and startups like Q-Control, for which this is their bread and butter. And of course, another important aspect that everybody talks about in developing these kind of national initiatives is the workforce training. And again, universities in Australia are starting to really move on this. We've got things from initiatives from individual subjects in quantum computing, and that's what we do at University of Melbourne, through to degree structures, Masters of Quantum Engineering, Quantum Technology, and so forth. And initiatives such as the Sydney Quantum Academy, and in Victoria, the Victorian Quantum Technology Network has been looking at this very closely for several years. So nationally, and this is my last slide, we've had a very comprehensive report from CSIRO on the economic opportunities that could arise from quantum technologies, and the imperative to really develop a national strategy for this. And we actually have the national strategy being developed at the moment. And there's been a lot of consultation for the national strategy, and we're expecting it to be launched shortly. So that'll be very interesting to see. From my perspective, Australia is in a kind of unique position, because since 2003 and before that even, there was a lot of activity in quantum science, and the ARC centres kind of allowed us to continue that, but scale up those activities across the universities and do that translation from the fundamental quantum science to starting to look at quantum technologies. Not just quantum computing, but also quantum sensing and quantum communication as well. And so I think it's fair to say that Australia is a world leader in quantum technology research and development. We have tremendous strength in this country. And you can just see from the centres of excellence there that are either directly in quantum technology, such as the Centre for Quantum Computation and Communication Technology and EQUIS, to those centres that are in and around the development of quantum technology. And beside the centres of excellence, we have a number of startups and other initiatives, as I've listed there. And this is by no means exhaustive anymore. It'll be hard work to really keep up on what's happening. So that's where I wanted to leave my presentation. As I said, I think Australia is really well placed now, and I think the next steps are actually going to be really critical for us.
Thanks, Lloyd, for an excellent introduction. I'm going to pass now to Eleanor, who's going to continue the conversation.
Thank you, and thank you also to Lloyd. I'd like to begin by acknowledging the traditional custodians of the lands upon which I'm coming to you today, the Ngunnawal and the Ngambri people. And in particular, I'm standing on the foothills of the magical Mount Majura here in Canberra, which is home to no less than a dozen sites of archaeological and anthropological and cultural significance. I'd also like to say that I've just taken a quick scan down the attendee list, and I see a lot of familiar names, and I'm a little bit sad not to be able to see your faces and to engage with you, but hello. So I'll pick up where Lloyd left off, and what I thought I'd do is come at it from a fairly prosaic perspective, and keep asking questions about what can we do with it. And Lloyd's done an amazing job of covering off on quantum computing. I thought I might just toss one extra idea in there. I happened to see in my nature alerts today that somebody has picked up the strong tradition of pioneering computer engineers in this case. There are stories of the engineers who made the very first Australian programmable computer, including Pawsey, after whom a society is named, after who a supercomputer in WA is named. He was a CSIRO scientist and he created CSIRAC. And one of the ways that computer operated was that they had acoustic delay lines. And so it meant that depending on the program you wrote, you could actually hear changes in the tonality of the humming of the acoustic delay lines. And so people actually composed and played music on Australia's very first programmable computer. I saw in my nature alerts today that somebody has composed and performed the very first music on a quantum computer. It's Lloyd, you'll be pleased to know it's the IBM one, and they've done a public performance of that. So there's quite a lot of interesting things that open up when you actually make computational technology widely available to a range of people. So that's just one cool thing that you can do with a quantum computer. But sticking more closely to the script, in terms of quantum sensors, the challenge with quantum computing is, as Lloyd has pointed out, to take objects and engineer them so that they are isolated as much as possible from their external environment so that they can actually display their engineered quantum properties. That means that they're exquisitely sensitive to their environment. And for the most part, those of us who are trying to build things that can do quantum computation, we spend much of our lives building control systems that isolate them from that environment. But you can actually flip that around and say, okay, well, so can I use that exquisite sensitivity for other uses? And the answer is yes. So you can build quantum sensors that are very, very much more sensitive to changes in particular physical phenomena than they would be through classical systems. And so these have been actually around for quite some time. Australia's chief scientist, Cathy Foley, made a significant contribution to the discipline through creating superconducting quantum interference devices, which have been commercially available for a very long time, and they are used both for minerals exploration as well as these days for water exploration as well. And they work because they are extremely sensitive to disturbances from the outside world. So it's an example of taking something and flipping it around and making that a useful product. There are many more types of quantum sensors available these days. And for example, the team in quantum control up in Sydney are working very hard on some sensors that show really amazing results. And Marcus and Lloyd both work in this world wearing different hats as well, and they can share with you a number of their examples as well. And then one of the other examples is quantum communications and what can you do with that. So quantum communications generally involves moving things around. So people traditionally talk about this from my world, which is around quantum optics and using photons, which have the singular advantage of moving at the speed of light. They also have the singular disadvantage of moving at the speed of light, which makes them challenging for computation, not impossible, but challenging, but it makes them fabulous for communication. They're not the only mechanism. A colleague once very famously in a meeting said, well, I've built a quantum memory that's so good I could stick it in the back of a truck and drive from Canberra to Brisbane and it'd work just fine, and that's quantum communication as well. But I'm hoping that he will forgive me for focusing mostly on optical-based quantum communication. So quantum comms are useful for three particular tasks. One is for distributing encryption keys, so cryptography keys, and those keys then will frequently get used for normal classical communication systems, but it solves a particular problem around how you actually share the secret key that would allow you to decrypt encrypted communications in the first place. And as a number of countries around the world are starting to think through what a post-quantum security and what post-quantum cryptography might look like, quantum key distribution is one of the potential solutions for that. Quantum communications is also good for moving quantum information around. And so you can use that inside of quantum computers. That's how you get the results of one calculation from A to B or other particular tasks. And it's what sits underneath all of the Star Trek inspired nomenclature around quantum teleportation and things like that. So it's useful for moving quantum information around in ways that normal communications can't. And the last task that quantum communications is good for is to move normal information, classical information around potentially more efficiently than you could using normal techniques. And efficiency these days is becoming more and more of an important conversation to have as people are starting to think about the vast energy consumption that goes into computation and communication and calculation. I think at last count, something like 10% of the world's energy budget is being consumed by computation. And a lot of that is the computation. It's not the internal communication that occurs within it, but anything that you can do to improve the efficiency is a powerful and valuable thing, because sometimes we're getting to the point where you can't just turn the sound up higher and keep going with those sorts of things. So that's a very prosaic and pragmatic way of thinking about these particular technologies, but hopefully they will stimulate some points of discussion. I'm very happy to unpack how these things work. And just to lay a couple of hooks for potentially subsequent conversations, there's been quite a lot of work, not just at the national level in Australia around how Australia might go through, develop a roadmap and strategies and things like that. There's actually international work going on, one of which is the World Economic Forum has created some quantum computing governance principles. The UN have put out norms of behavior in cyberspace, which touches on quantum computing when you start to talk about cybersecurity. And these days, everybody is talking about critical technologies and critical technology lists, and quantum computing appears on those lists all of the time. And one of the reasons for that is because to appear on a list, a particular technology has to be incredibly important to a country, both for its security future as well as for its economic future. And I'm hoping that Lloyd has convinced you in his arguments about particularly how quantum technologies are important for our economic future as well as our security future. And so on that note, I'll close. Hopefully I've left enough hooks for some conversation, and I'll pass back to Sandra and Marcus.
Thank you, Eleanor. And can I just remind people to post some questions, because I can't see any yet in the Q&A, but otherwise I'll pass over to Marcus to give a bit of an opening statement.
Yeah, thanks a lot, Sandra. And to Lloyd and Eleanor, you've done a great job providing the very broad perspective of the technology, its implications, in national, international landscape. So what I might do is I might focus on and go narrow and provide a deeper example of some of the activity that is happening. And I'll focus on quantum brilliance, and I'll talk about the quantum brilliance story, what we're trying to do, who we are, who are the people that work at quantum brilliance, and then go on to talk about what are the things that we're doing, what's the products we have, how do we engage with customers, and how does that take us towards the place we're trying to get to. So firstly, who is Quantum Brilliance? So Quantum Brilliance is an Australian-German company. We are distinct in the quantum computing landscape because we're pursuing quite a different vision and trajectory in developing a quantum computer. Most other companies are seeking to develop a quantum mainframe supercomputer. So that is a large, complex, highly sophisticated, very powerful quantum computer that competes with supercomputers or very large high-performance computing infrastructure to solve really tough problems. Quantum Brilliance, we're going in a different direction, is that we're building quantum accelerators. So much like you have graphics accelerators in your laptops and PCs, and much like people cluster together GPUs to solve certain problems, we're building a quantum accelerator, which is a small, compact quantum computer that seeks to deliver an advantage over similar classical computers in select applications, just like your graphics processor enhances graphical processing in your classical computer. This and thus our aim is not to outcompete supercomputers using one of our devices. Our aim is to outcompete a single CPU or a single GPU using one of our devices, and then cluster them together to compete with many CPUs and GPUs in select applications. The reason why we pursue this different technology is because we are taking the natural advantages associated with qubits and diamond. So diamond is our quantum material that we exploit in order to develop this technology. Diamond quantum computing isn't something new. It was first proposed in 2001. There was a great deal of gains over the last 20 years in terms of the development of the technology, right up to simulating molecules, demonstrating early simple error correction codes, all the basic sort of proofs that a quantum computer have. But diamond quantum computing fundamentally hit a challenge when it came to scaling up the number of qubits. And so that's one of the big challenges that Quantum Brilliance is seeking to address. But what are we doing right now? Well, we're a full stack company, which means we're developing both software as well as hardware. We have two different types of software offerings. One is Crystal, which is our software development kit, which was released and announced at Supercomputing Asia a couple of days ago. So if you haven't checked it out, check out Crystal. I'll pop a link in the chat below. And that is a unique software development kit that allows you to start to develop applications and demonstrate how you might use quantum accelerators to accelerate a variety of different tasks in edge computing, such as robotics and autonomous systems, in satellites, or in communication systems, as well as how you might orchestrate and manage massively parallelized quantum computers. So if these are topics which interest you, then make sure you check out that SDK. It's unique in how it enables you to pursue those application ends. One of our other products is a quantum emulator, which is a very high performance emulator, which encodes all of the details around our current and future hardware, which means that when you use that emulator, you can faithfully trust that the performance you're predicting is indeed the current performance of our devices and the likely performance of our future devices. So you can really say, will this quantum accelerator deliver an advantage over your classical computer? That's an incredibly powerful tool, because that, combined with the SDK, is enabling a variety of people to pioneer applications for quantum accelerators. So we're working with companies such as Thales, such as NVIDIA, such as a variety of universities in Germany, machine learning companies here in Australia, the Australian Defence Force, to really push forward applications in edge and massively parallelized quantum computing. Some examples there is in speech-to-text conversion at the edge. Currently, to get high accuracy speech-to-text conversion, you actually need considerable computing power to do it, which is not practical if you're trying to put that into a mobile edge device, such as something on a vehicle or something in a robot that you as a human are trying to interface with. What we're working with an Australian machine learning company and the Australian Defence Force is whether quantum accelerators could give that big uplift in computational power density to deliver that gain in accuracy in speech to text, and thus make it a real technology that the Australian Defence Force can trust. Another application we're dealing with is optimizing manufacturing. So this is robotic manufacturing in Germany, and we're doing this in conjunction with Thales and the Fraunhofer Institute. And we're seeking to understand if a cluster of quantum accelerators can be used to optimize various sorts of pick and place and assemble tasks on a future manufacturing line. And that project is underway. But it's not just a software and emulator. Quantum Brilliance is also distinguished by the fact that we have early hardware. So right now we have a desktop-sized quantum computer, which is operating in the Pawsey Supercomputing Center. It is deployed there. It is integrated in the computing racks alongside all the other CPUs and GPUs, and it is currently undergoing a field trial where we're benchmarking the performance of the device, and we've already demonstrated a variety of simple quantum algorithms on that device. There's much more work to do to make that into a device that delivers computational capability, but it's a key proof of technology that you can actually package and deliver something that is a quantum accelerator and integrate it into an incredibly challenging environment, which is the floor of a supercomputer alongside all the other computing instruments. Now, I wanted to talk a little bit about who are Quantum Brilliance. Who are we? What do we look like? What jobs do we come from? These sorts of things. So Quantum Brilliance is around 90 people, a bit over 90 people, about half, a bit over half in Australia, spread across Sydney, Canberra and Melbourne. And then also in Germany, spread across Stuttgart and Freiburg. Those people come from a variety of backgrounds. A quarter of the technical staff are quantum physicists, but the vast majority are actually very, very highly experienced and highly talented engineers who have come from predominantly electrical and photonic engineering background, as well as computer science and software engineering. And so these engineers are the future of the quantum industry. It's very important to understand that that's actually the quantum workforce, the majority of whom are our best engineers rather than quantum physicists. And so alongside those people are also great business people who've come from commercial backgrounds, who really understand how to build business models, how to build and deliver products, how to interface and gain the financing and the customers required to create a sustainable business. And that's ultimately what countries like Australia and others are after. They're after the development of quantum computing or quantum technology companies that deliver economic prosperity and security and are sustainable organizations. So the last thing I'll end on is then what about Victoria? So we're at the Victorian panel here. So recently, Quantum Brilliance was fortunate to announce one of our most recent capital raises alongside Breakthrough Victoria. And Breakthrough Victoria had invested $8 million as part of a larger $26 million raise that we had done. Victoria has a profound opportunity in diamond-based quantum technologies. It is a leader in diamond-based quantum sensing. Lloyd was one of the key proponents that built this capability over decades in Victoria, and that is now spread across a variety of institutions in Victoria, across Melbourne University, RMIT, Monash, La Trobe, etc. And it extends all the way from the foundational material science around diamond right through to developing quantum sensors for applications. And the investment of Breakthrough Victoria in Quantum Brilliance was really about doubling down on the already multi-million-dollar investment that Quantum Brilliance had made in Victoria, which was the creation of the research hub for diamond quantum materials. And in conjunction with La Trobe and RMIT University, that follow-up by Breakthrough Victoria has enabled us to extend and grow that research hub, as well as turn our attention to working more broadly within the diamond quantum technology ecosystem that is in Victoria. And we look forward to doing that and interfacing across both industry and university. So with that, Sandra, I'll pass back to you.
Thank you, Marcus. And we'll now try and have a bit more of a broad discussion. And I suppose my first question relates a little bit to what you were talking about then. You've talked a lot about what's happening inside Victoria. And Lloyd talked a little bit about also the national strategy for quantum technology. So I suppose I'm interested in thoughts from all three of you as to how important it is to have a national strategy in this place and take a national strategic view. You know, we have a national hydrogen strategy. We have various other policies that are national. How important is it in this context to act nationally rather than just at a state level? I don't know who wants to go first, perhaps Lloyd.
I might go first and just declare that I'm actually on the National Quantum Advisory Committee. So I will say, in any case, it's incredibly important. I think a lot of what we need to do in developing quantum technologies, whether it's quantum computing, sensing, or communication, involves scale, not just scale in the devices that you're actually making, but also in the expertise that you draw upon and the resources that are available. And we see this with Quantum Brilliance as an example, that, you know, they're spread across Australia and Germany, and within Australia across a lot of different geolocations. And I think that is the story of quantum technology development, this ability to scale the interactions across not only where people are, but what people are doing, because we need to connect the end users with the quantum physicists and the quantum engineers and so forth in order to make progress. And, you know, we are a relatively small country and we need to do the absolute best and optimum that we can do with the resources that we have.
Mm-hmm. Marcus or Eleanor, do you want to add to that?
So I would say that it's just doubling down on what Lloyd had said there, and that is that no one state has all the parts, but they have their distinguishing strengths and their contributions. And as a result, if we can deliver a strategy where we can reinforce those strengths and then reinforce the interactions between those strengths across the national system, then we will be able to prosper in this field. And that the opportunity in front of Australia is profound. We are players on the world stage and are bringing something that other countries very much want. That's why you see lots of British and Canadian and Americans coming and visiting us, trying to take our talent and trying to engage with our companies and these sorts of things. And so if we get ourselves coordinated, we invest in those things that make the big difference, that bring us together and reinforce the strengths, and I think we can be successful.
Yeah, I think one of the keys there is I think we all agree on what in terms of, national strategy and coordination. It's really at the moment about the how. How do we do that? I think reading where things are at the moment, it looks like there's a lot of state-based activity happening. But what I hope, and when I'm involved in these things in Victoria through the Victorian Quantum Technology Network, I hope that we always have a sense of how do we scale those state-based initiatives and allow them to interface with other initiatives around the country, or indeed scale just simply to other areas in the country. So I look forward to seeing how that debate goes in the next few years.
And I guess I would amplify those comments in the sense that Australia, well, in fact, the whole quantum technology world, we stand at a moment where we could potentially make a new world, and we have an opportunity in Australia to be part of the people who make that new world. And the main thing that we're going to have to do is is have the courage to actually step into that opportunity together, because if the only way we can do it is together, and it is going to require a bit of courage. And the really wonderful thing that I think we've all seen over the last couple of years is actually we're having those ambitious conversations. That's just like that's really exciting. And I guess the thing to do now is to harness that. I guess I was on a panel at Quantum Australia last week where one of my fellow panelists said that it's really boring when everyone agrees with each other. So I'm going to try to toss a little bit of sand into the oyster. And ASPE have just brought out a critical technology tracker today that looks at, that does an analysis that tries to speak to some of the issues globally around where all of the various critical technologies sit, that list of 44 critical technologies, which country is doing well, what does that mean globally? And Australia does not appear in the top 5 for any of the 5 quantum technologies that they've analysed. So that's worth unpacking a little bit, I think.
Did they give you an indication of how they measured that?
Yeah, well, so there's the interesting question. So it's and I think it's come out today. So I think if nothing else, we can generously say it's going to trigger a lot of debate and perhaps some contest around this. This one's a bibliometric analysis. It's not how much money is going into the D and the applied research end. It's a bibliometric analysis. And they do it, one of the analyses is essentially just basically the percentage of publications that you have, that a country has in particular areas. One of the interesting things about it is they also talk about the concentration or monopoly risk for particular technologies. And essentially what they do is they say, if a particular country has 10 of the top most published universities in a particular technology discipline, and they've got a 3 times advantage, that means that that technology is at high risk of being concentrated and going into a monopoly in a particular country. It says all of the things that you would expect, which is that there are 2 technological superpowers in the world, one being the US and one being China. There is a second tier of players that sits underneath that. And the headline that is appearing in most of the newspaper reports at the moment is that China has the lead on most of those and the US is coming second on most of them. The fascinating thing is that in quantum in particular, it's very low concentration. So it is up for grabs.
And to build on that, I think you've brought out this issue that we will need to compete and to work hard in this space if we are going to be excel and particularly protect that, avoid that sovereign risk problem. And that brings us to one of the pointy questions, which is how do we develop the workplace skills? I was interested that Marcus pointed out that this is predominantly what we need as engineers, but I think there's a big skill set that's going to be missing. So are we doing enough in Australia to meet the demand? that industry, business and government will require from these skills going forward? Perhaps if we look at that one first, and then I see that Anne's posted a question that's relevant to this as well. So I don't know who wants to start on this topic. How did we develop those skill sets? And again, Anne's comment there is, do we position that at postgraduates or are we aiming at undergrads? How do we tackle this problem?
I'm happy to jump in. We've been doing this for a while and thinking about it for a while. So in quantum computing, which is the educational area that I've been specifically involved in, back in 2016, we were starting to think, okay, what would a subject look like that would train students in quantum computing? And obviously, you can take a very small cohort from your physics school and train them up very quickly because they've done years of quantum mechanics. But really, what we need to do is train people who have no background in quantum physics to be able to not only program a quantum computer but get the best out of it. Possibly in ways that a quantum physicist wouldn't be able to do because they don't know much about programming. Well, we do, but we probably don't program that well. So we designed a subject that was aimed at the master's level, and it was to be taken by students across, any faculty, so computer science, finance, and across the science faculty, with only sort of a moderate background in mathematics, so complex numbers and matrices and things like that. And that's been enormously successful. If you can actually design the syllabus in such a way that you bring people up very quickly from zero knowledge about quantum information to what you need to know to be able to program these systems. And that led us to be able to then translate that sort of subject to the undergraduate level. And we have a second year subject that's sort of similar in vein, and it attracts a lot of people from across all faculties. From there, I've been looking at how to do that at the STEM level. So for many years now, I've been sort of creating these modules where high school students can sit down and also get the principles of quantum computing and start doing some programming within a few hours. So these are special project modules that have been quite successful and quite enjoyable to see how the students take it up. So I think there are certainly ways to do this, and that's the way that we focus on how to train the workforce. But of course, you can go straight to training quantum engineers, and that'll be needed as well. I think we need probably a much broader spectrum in order to get the workforce to a level that's needed and indeed exportable, perhaps, which would be really important.
Yeah, Marcus, do you want to comment on this? I know you mentioned electrical engineering as being the sort of people you're looking at. What skills do you think we need?
Yeah, so as a consumer of the educated, what I would say is that our needs right now are actually to convert people from other disciplines into quantum technology. So we as a company invest and spend a great deal of time taking, top-notch software, photonics, electrical, electronic engineers and turning them into quantum engineers. And that's about teaching them the basic principles of quantum technology. And then more specifically in their discipline, then how does that feed through to the key considerations and factors that they have when they're designing and interpreting the technology that they develop. But this is something which is challenging. So, in our case, we are seeking really experienced semiconductor device engineers, and there's not many of those globally as it is. And we need to find those people and then convert them across to quantum. So it's not just a paucity of talent within quantum, it's that depth of talent across engineering in those supporting disciplines that will feed into quantum technology. And so I would see that as being our real immediate need.
And Eleanor, I thought you were trying to type an answer there, but you would have commented on this as well.
I was just going to reply very specifically to Anne's follow-up. Just really briefly, couple of years ago, a bunch of us in IEEE, so the International Electrical Engineering peak body, came together, and we put together basically the beginnings of a body of knowledge for quantum engineers. I've lost track of where that's gone over the last little while since I've been out of universities, but that still is there. I think everyone knows that UNSW has a quantum engineering curriculum, and our colleagues at, I think, at the University of Adelaide have experience in creating MOOCs that speed up upskilling for teachers around maths skills. That might be a good place to lever to start to talk to work on some of the things that you're talking about. But there are bodies of knowledge out there that have been identified. And just to Marcus's point, speaking as a former dean of both engineering and computer science, I could speak for hours about some of the interventions that I think need to happen in Australia around engineering and computing, and how to deal with that particular workforce issue. But in the interests of time, I will just cut myself off.
Okay, and then there's a question there. I don't know whether you guys have got the chat open, because I don't know whether I understand it, so I'm going to ask you. There's a question from Madan about, with different qubit hardware technologies, proprietary development kit around, are there possibilities for future hybrid quantum computing to leverage the knowledge resources for better results and utilization? Anyone want to have a go at that?
I'm going to point across to Marcus because the diamond approach has that possibility of both a matter-based qubit and photons. So I don't know if you're thinking about that already.
Yeah, so if I understand correctly, this is about hybridizing different qubit technologies together in order to create quantum computers. So this is certainly a topic that a lot of people are pursuing and thinking about, which mainly around how to do the buses between quantum computing chips, or between distant quantum computers. And that's really where some sort of form of transduction is needed to go from things like superconducting qubits or spins or these sorts of qubit technologies into a qubit that can travel, like what Eleanor was talking about with photons, and then back again. And that is both key for scaling up across multi-chips, as well as having that long distance quantum networking in the future. So people are definitely thinking about this as a problem. It's one of those things, however, that will follow on behind, I would say it's going to follow on behind the pioneering of a single technology. So a single qubit technology that goes as far as it can. And that will really be what drives the big advantages, just like you see IBM is pushing ahead with superconducting qubits and these sorts of things. We're at 433 now. And that will lead the way. And then these other technologies that enable you to connect together will follow, and they will find their place. Whether they really deliver an advantage through hybridization over those pioneering technologies, we'll have to wait and see. Are they needed to create the ultimate dream of a quantum internet? Yes, they are. But just like with the classical internet, I dare say it will come a bit later than those pioneering devices.
Yeah, I point out there is actually an important hybridization already happening in this technology, and that's between quantum computers and conventional computers. It's becoming quite apparent that for these larger scale quantum compute type applications, you really need a supercomputer there as well to do certain tasks. And it's a fascinating confluence that's happening now. We always knew in the far future, where you have massive amount of quantum error correction, that you have to do a lot of associated computing tasks. But what people are finding now is that the certain combinations of the quantum computing processor and a classical processor or a conventional processor may actually be a path to quantum advantage in the near term. So exactly how you bring those two technologies together is going to be a fascinating and fast-paced story over the next few years.
Yes, I think we're all going to struggle to keep up. There's a question here about the ATSE tracker, and I think, Eleanor, you want to answer this question about why they're showing there's only 27 people employed in quantum computing on the tracker.
Well, so actually I was simply going to contribute to the conversation.
Yeah.
There's the problem.
Indeed. The piece of courage that ASPE have done is put this data out there to trigger a conversation. I think some of these numbers are going to be contested. Some of these numbers, I think, need to be updated because some of the conclusions in the spaces that we know a lot about just kind of feel a little bit they're not intuitive. Let's put it that way. So to anonymous attendee, please feel free to reach out to ASPE to politely suggest that there might be an opportunity to update and refine their numbers, because actually the more that we help them to update their numbers, the better it is for all of us in terms of understanding our having situational awareness as we go.
Yep. I might change the topic slightly, though we are running out of time. What ethical issues do you think are going to be raised by this shift to quantum computing? Are there any ethical issues? I think, Marcus, you were going to comment on this one.
Yeah, so not just quantum computing, but quantum technologies more generally. What I say is that fundamentally, quantum technology are enabling technologies. They are enabling us to do better sensing, to do more secure or enhanced communications, or to do better, to do faster or more powerful quantum computing. So as a result, they don't necessarily, my opinion is that they don't necessarily bring any new ethical questions. It's more that they are accelerating technology and thus perhaps bringing old ethical questions into light that have once been dealt with, but now we need to reconsider. So one example would be around, let's say, quantum key distribution, which purports to be a way of having a truly physical assurance around your ability to distribute encryption keys and thus communicate securely with each other. That raises the old debate, which is who really has the right to have purely private conversations that can't be decrypted? Do we, as part of a society, actually give way to that right because we rely on our police and security forces to detect threats that might be within us or external to us, and therefore we give away a bit of privacy in order to have that security? So that's an example of an old ethical question, which has been brought into new light through the potential of these technologies. Quantum sensing, similarly, if you have new ability to surveil and reconnoiter areas, then does that lead to now a fundamental change in what we believe is our right to, again, privacy in this instance? I don't think so. It's just brings in, here's a new technology, let's develop it responsibly within the guidelines and norms that we've had developed previously technologies. And so I think it's more of a question of responsible innovation rather than of new ethical dilemmas. But I'll hand over to the other panelists.
Well, I'm just saying we've only got 2 minutes left, so I'm going to give Eleanor and Lloyd, respectively, 60 seconds each to summarise, say anything else I'd like to say.
Okay, look, I'm just going to riff off Marcus really quickly, just to pick up on that thread around the UN norms of cyberspace. There are 11 of them. 9 of them are about positive things that we should be doing to make life better for everyone, and there are 3 red-coded ones, which is we should not do that. And to Lloyd's point, quantum technologies become a tool in cyberspace rather than necessarily changing those norms.
And Lloyd, you get the last word.
Oh, I get the last word. I was going to bring up a new topic, which was the development of standards of the technology. I think is something that really needs looking at an international level. And if you think about, videotape technology, VHS and Beta, we have many contenders now for different technologies. So I think that's going to be a fascinating conversation going forward.
Yeah, well, thank you. I think we could all continue to talk for a lot longer, and you guys are welcome to stay back and chat. But I was told to close this precisely at 7:30. So I will finish up and let everybody go and get their dinner. I would like to thank enormously our 3 speakers, Eleanor, Marcus and Lloyd. I think you've done painted a wonderful picture. It certainly got me excited about the potential in this area. So thank you very much for your time. If I briefly mention that our next event that the Victorian Division is holding will be in person. We're going back to a real room, and that'll be Sue Barrell is coordinating a seminar regarding research infrastructure, which touches a little bit on some of the topics we've covered today. So, but we'll also cover things like the exciting work going on in the Stawell gold mine. So thank you very much for your time. We really appreciate it, and we will sign off now. So, and look forward to seeing you at a future event. So thank you.
Thank you, everyone.
Thank you. Bye.